Okay, so exam 2 review. Okay, so the question is number 4 on the practice exam. And it says, it's towards the end here. Was that? Oh, yeah. I'm just reading through the question. Yeah, towards the end here it says, okay, so for a liquid-liquid system, what are the compositions of the two phases once the system reaches its final temperature? So the drawing is the spinodal and binodal curve. I think this is from the homework exactly. So we have temperature. We have one line that looks like this. And then on the exam it's dashed, but I'll just do it in a different color so it's easier. Okay, so we can walk through this one. Part A is label the binodal and spinodal curves. Okay, so which is the binodal?
Top one.
All right, binodal, which means this is the spinodal. So we can go through the whole problem then. What is the upper consolate temperature, or how can I identify it?
You can either just think of the peak temperature, or you could say that gives dG dx equals dg squared x, or dg squared x, or second derivative of g, and the first derivative of the gx is 0.
Correct, because that is the first point where you have a unstable fluid. So the upper consolate temperature is given by dg dx1 is equal to d squared g dx1 is equal to 0. Because if we were to, let me go to the next slide over here. If we were to draw out the Gibbs free energy, of a mixture as a function of one of the compositions, right? If it's fully ideal, right, we have it approaching the axes here with an infinite slope. That's because of the entropy of mixing, right? If you put one molecule in a sea of another molecule, then it just it gains effectively an infinite amount of entropy, right? Because you've taken one molecule and you've given it an infinite amount of space. So the point at which we start to have a phase transition, obviously if we have a curve that looks something like this, then we know we're going to have a phase transition because we have stable, unstable, and stable regions, where the unstable region is given by the curvature. In this case, it's less than 0. Right, and this is a direct consequence of entropy always having to be less than 0. The curvature, rather, sorry. Because remember, when a function is concave, let's talk about the converse here, right? When we have entropy as a function of any variable, right, it always has to look like this. Because in a concave function, if you take a current state and you split it sort of into two little teeny little microstates there, this results in in this case it'll be a lower entropy. If the opposite were true, and entropy looked like this, anytime you would split into two microstates, you would have a higher entropy, in which case the system would just sort of catastrophically fall apart. So in order for the universe to be stable, and that equilibrium is at maximum entropy, you have to have the curvature of entropy such that it's like this one here. It is concave. So conversely, if we expand that to the Gibbs free energy, the Gibbs free energy has to be convex. If the Gibbs free energy is concave, like it is here, with a negative curvature, then we know it's an unstable fluid. Right? Same logic applies here, that if we were to have any small perturbation in an unstable fluid, it would lower the Gibbs free energy or increase the entropy, and that's where you have sort of this catastrophic separation following that spinodal decomposition video that we watched. Okay, so the point at which the phase transition first occurs is if we keep going into a region where we have a smaller region of instability. And eventually you'll get a point that's sort of a magic, right, where you have the criteria, where you have an inflection point and a minima at the same point. And this is going to give you your upper consolid temperature. Or you could have a lower consolid temperature, or you could just be a function of a number of different parameters, right? But for phase equilibrium, or the phase separation in the liquid-liquid system, this is how the curvature of the Gibbs free energy changes and dictates the phase behavior of the system. And again, this is exactly the same kind of logic that we applied when we talked about vapor-liquid equilibrium for a single component, right? Using the an equation of state. We looked at dP dV at constant temperature, right? A PV isotherm. And in this case, I have to remind myself, we had curvature like this, and so this is unstable, so this is negative. So this has to be greater than 0. Wait, no, less than 0. See, and I ruined it. Okay. Here's a quick recap of liquid-liquid equilibrium. So going back to the question then. That's our upper consolid temperature. The next part of the question is, what is the mathematical criterion for defining the Spinola region? Well, we covered that already. So in the Spinola region, this is where d, the second derivative of the Gibbs free energy, is going to be less than 0. That is the criteria for the Spinola region, where we have an unstable fluid. If we were to define some temperature, how could I read out the composition of my two phases?
Just go to the Spinola curve and just find the points on exactly right there, and then.
Yep. It's the binodal curve, right? The binodal curve is the coexistence curve. This is the one that we solve for with the liquid-liquid criteria. That's how we define the binodal curve, the phase coexistence curve. The analogous curve to the binodal for vapor-liquid equilibrium is just the bubble and dew curves. That's an analogous scenario, right? Because this equation comes from matching the partial fugacities across the phases. And the solution to that equation that balances out the activity coefficients, that balances out the composition, that solves our phase equilibria curve. Now, this is exactly the same equation that we're solving for in vapor-liquid equilibrium. The only difference is how do we approximate the partial fugacities. So the bubble and dew curves are more or less analogous to the binodal curve in this liquid-liquid phase diagram here. The spinodal is a little bit different, but yes. So we would just read them off. So in this case, we would have x of 1, we could call it phase 1, x of 1 of phase 2. If this is a two-component system, 1 minus x of 1 of phase 2 is equal to x of 2 phase 2. 1 minus composition of x of phase 1, x of 2 phase 1. Now I could switch which one's phase 1 and which one's phase 2, it doesn't matter. So the more general term is I should call this one which phase, what component is this phase enriched in? 2. So I would call this the component 2 rich phase. So if we knew what it was, then we could call it the, chloroform rich phase or something like that. And this is the component 1 rich phase.
I just have a quick question. Realistically, how often, when you're doing liquid-liquid equilibrium, is the one constant McGruder's equation actually actually valid? Or
Oh, probably never.
Okay.
Just like how the van der Waals equation is never used either. Liquid-liquid systems are exceptionally complex. And so you guys see on the homework, right? So I didn't get a very good fit of the NRTL model to the VLE data for that water THF system. But liquid systems or non-ideal systems can be very, very complex. So the one constant Margulis is like the van der Waals equation. It's a nice, fun equation to play with where you can very easily manipulate it. But anything more complex, it starts to be really onerous. To go from a model of the Gibbs free energy, right? So just as a quick recap, right? We went from some model of the excess Gibbs free energy, some function of a bunch of different parameters, and then we take this information and we want to calculate the activity coefficient. But we define the activity coefficient right as the partial molar Gibbs free energy for species, partial excess Gibbs free energy for species I, right? That's how we define the activity coefficient. And if you recall, anytime we had a overbar parameter, this was the direct calculation of n theta under bar. So in order to derive the activity coefficient model, right, we had to have some overall function to fit experimentally measured excess Gibbs free energy. And what we also learned on the homework is that you can't really just measure Gibbs free energy. There's no magic tool to do that. Right? We can measure pressure, temperature, and composition easily. We can measure volume too. Right? But we have to assume some type of a model in order for us to actually calculate the excess Gibbs free energy, right? And in that model that we assumed, we said it was a non-ideal liquid phase but an ideal vapor phase. But we could have assumed a non-ideal liquid and a non-ideal vapor. But then we would have to have a way to calculate the fugacities of the vapor phase in order to estimate what the excess Gibbs was like. You know, what is the contribution to the non-ideality, for example?
I got a question.
Yes.
Partial molar property, isn't it NGA does not equal A, or?
Oh, yeah. Correct. So in the one constant Margulis, right, we did a Redlich-Kister polynomial as this function here. And this is just a convenient polynomial that fits all the criteria and properties that we would see experimentally in the excess Gibbs, right? That it's pure species, the excess should be 0 because it's a pure species. There's no mixing properties at all, right? And so that particular polynomial that we fit was A, x1, x2, right? And this is a Redlich-Kister polynomial. With one coefficient, but we can have a much longer, Redlich-Kister polynomial. Or in the case, for example, of the excess enthalpy that we had in the homework, it was like a 5-parameter Margulis polynomial. Right? These are just empirical fits that have the properties that at pure species, there's no mixing properties. Because when we try and calculate the infinite dilution properties, if it doesn't go to 0, there's really, really big problems. Okay, so the last part, really, of this exam question is saying, if I have some mixture up here, right, and I quench it down to a low temperature, how do I know what the two phases that separate are, and what temperature does the phase separate at? So we just march our way down, lowering the temperature. I hit the binodal curve. This is where I begin to phase separate. So when I start to phase separate, what is the composition of the new phase that forms? How can I tell? I just do the same thing I did before. I draw it across. Right, so the same logic that applies to bubble and dew curves for vapor-liquid equilibrium also applies to liquid-liquid equilibrium. Right? At equilibrium, I have a constant temperature, a constant pressure, right? So in order to have a constant temperature, I have to draw a horizontal line. Where that horizontal line intersects with the equations that I care about, those are the solutions to my systems of the equation. Right? We saw this a lot with the bubble and the dew curve, figuring out, what is the composition of the two phases in a TXY diagram or a PXY diagram or so on and so forth. Same exact logic applies to this liquid-liquid phase diagram. Yes?
So just to kind of make sure, if we say we were to drop down into the Spinola region, it still stays separated into the same composition, but just the way you get there is different, right?
Correct. Yep. So if we were to then, for this example up here, if we were to drop ourselves into this condition, our two compositions would be given by here and here. If we were to drop ourselves down into this composition, in the spinodal region, we would still phase separate following the phase coexistence curve, also called the binodal. Now I could ask, what is the maximum supersaturation that we could create? That would be right here on the border. So we would be supersaturated by that amount. Right? Because if you remember, in the binodal region, here, I shouldn't have used orange, but anyway, in the binodal region, this is where we have a stable fluid with a convex Gibbs free energy, right? Positive curvature in the Gibbs free energy. And when you have a convex function of the Gibbs, that means if you split it into two different little phases, you would have a higher Gibbs free energy. So in this region here, there is a energetic barrier to phase separation. And that is the thermodynamic underlying principle behind supersaturation, or superheating, or subcooling. Yes, question?
So now, actually, I got a question about this. So now if we, superheat something and then it, rapidly boils in the thermic process, and same goes for if we have a supercooled liquid and we cool it. Actually, I believe that would be exothermic. But when we have the liquid, how big is it? Is it going to be an endo or exothermic process? Will it?
Whether it's endo or exothermic for a phase separation, I don't think there's a good general rule for that. I would say for the most part, most mixing processes are going to be endothermic. So if you're demixing, probably going to be exothermic then. But no, there's no generic rule for that. But the main issue is that it's not this terminology used more in reaction discussions, but we can call it. You've heard of the reaction coordinate, right? And that's how catalysis sort of works. What we could think about really is that if we look at the Gibbs free energy as a function of time for a phase separation process, right, this is of course in the binodal region, we're going to be starting off at some Gibbs free energy. And that Gibbs free energy is going to be of a stable fluid. So in theory, if nothing changes, it could exist there. It's not at the lowest energy state that it could be at. But if it's precipitating in the binodal region, then we know that there's going to be some energy barrier to potentially form a new interface or form a new crystal structure or create a new phase. Right? And this is what we talked about with surface tension. Right? When you get a bunch of molecules together and they want to form a new phase, they create an interface. That interface has a discontinuity in how the molecules interact, which causes some sort of an energy barrier to exist. So that barrier is going to have some sort of threshold. But then we know in phase separation, we are always going to have a lower Gibbs free energy. Otherwise, it wouldn't phase separate. Right? If we had an alternative scenario that went like this, that's not going to be a spontaneous process, right? Because that's going to raise the Gibbs free energy. So when you're in the binodal region, this barrier here exists as a result of forming a new interface and forming a new phase. Which is why if you have like a heterogeneous nucleation process, so for example, if I have a supersaturated sugar water or salt solution, and I flick in one single little crystal, that crystal has already gone through the struggle of creating that new interface. So then all the molecules that want to precipitate out, they don't have to create a new interface. They've already got one there to stick onto. So if you can imagine, if we just think about this in a 1D process, if this is the interface, if I have molecules that want to stick to it, I'm not actually really increasing the surface area of that new interface. Technically, yes, there is some barrier. In a 1D scenario, you can see there's no barrier, right? Because the energy here is related to the surface tension. So in a 1D system like this, adding new material to that crystal surface isn't technically increasing the interfacial area. Interfacial area has interfacial energy, and we call that the surface tension. In a 3D object, yes, as you increase its surface area, right, its volume also increases, or so its volume increases, its surface area increases, but it's much, much smaller of a barrier than a homogeneous process creating a sphere or new crystal all on its own. Bit of a throwback to what we were talking about in the earlier phase separation. Okay, any questions? What else we got? Yeah?
About the supersaturated point.
Mm-hmm.
So will it not stay separated there, or does it just take like more energy?
So if we are in the binodal region, this drawing's getting a little crazy. So if we're in the binodal region here that I've scribbled in orange, if there are, it will still phase separate, right? What we're concerned with our solutions are infinite time equilibrium answers. And so for our purposes, we are always going to be going to the binodal region, right? But in terms of a practical perspective, there could be kinetic barriers to the phase separation process. So for example, if we relate it back to a distillation column, when we talked about our XY diagram and counting out the stages of the distillation column, we were assuming that every single stage, which corresponded to a tray in the distillation column, gave us, a whole new equilibrium relationship. But in reality, there's mass transport limitations, how big are the bubbles, what's the surface area contact. There's a lot of other complexities for a real process that we can conveniently neglect.
Also, we're using a reflux switch.
Makes you have no product.
Yeah.
Right? So basically, in practical terms, right, even though you think you should have crossed the threshold, there may be some sort of a barrier for that precipitation. So if there's a really high surface tension between the two fluids, that might mean that there could be a barrier that needs to be overcome. But that can be overcome by providing nucleation sites, for example. Yeah?
So the areas outside of the binodal curve are areas where you're like under your saturation solution, and then when you get into like the binodal curve is almost like a saturation curve where inside of it you're now super saturated, and then once you get reach this binodal curve, that's where you can no longer super saturate it any longer.
Exactly. Yep. So let's say I had a solution of pure component 2, right, at this temperature. And then if I started titrating a little bit of component 1 to the system, I would be marching in this direction, right? This is a one-phase fluid, one phase, one phase, one phase, boom, 2 phases at equilibrium. But if I'm titrating really, really quickly and sloppily, like I do in organic chemistry, I would maybe get over here and say, teacher, this is the solubility point, right? But in reality, if you were to do this infinitely slow, right, which is all of our thermodynamic calculations, if you were to titrate, this is the point where you would start to form a second phase. So the solubility of component 1 into component 2 is given by that point right there. So then if we were to then, let's say, plot out the solubility as a function of temperature, right, it would just basically be taking this curve here and sort of flipping it on its side, and it would kind of look like that. Does that make sense? Because if I were to use this temperature down here, much less soluble than if I were to go up here, and eventually at some point, they are infinitely miscible. And the solubility is, well, infinite, basically. Or it's not, well, I don't know how you want to describe it. They can completely miscible solutions. How do we feel about this? So this covers a large part the liquid-liquid equilibrium recap. The only thing that I would like to add in addition to what we talked about for the graphs on liquid-liquid equilibrium is just to remember where we came from. So in liquid-liquid equilibrium, our starting point is, of course, our partial fugacities. Now, for liquid systems, we approximate the fugacity, or the partial fugacity, like so. We have introduced no assumptions into this process. We have, of course, introduced a slight amount of cyclic logic, right, because we define our activity coefficient as a scaled version of, let's see, G over bar I excess over RT, right? RT, ln again, yeah. Right, so we kind of cheat a little bit in the sense that we set up our partial fugacity of the liquid based on defining the activity coefficient, which is directly related to the excess partial Gibbs. But what this allows us to do is to come up with activity coefficient models. Right? It's a way that we can organize, store, and tabulate real experimental data. And from here we talked about the Margules. You know, there can be one constant, two constant. We did the Van Laar very extensively. In the homework, we just talked about the NRTL. We have regular solution theory. Then we have more advanced ones like unit quack and univac and univac, FAC. I think that's how it is. Tons of different models. Some of them are predictive. Some of them are strictly empirical, right? Like the Margules equation is just 100% empirical. We just chose an arbitrary polynomial and said, let's just fit it with the polynomial, right? Regular solution theory is fully predictive. Uniquac is combinatorial, but it also has some tunable parameters. So basically what your molecule looks like, you can kind of add little bits and pieces. Unifac is the same thing as Uniquac, except they have used correlations of similar chemical properties to turn it into a predictive function. So Unifac is sort of a semi-empirical approach. But in all these things, these are just different models, and there's more than we can cover in a class. But basically, they all start off with the assumption of what does the functionality of the excess Gibbs look like, based on how we expect the entry to behave, how we expect the enthalpy to behave, or maybe just a strictly empirical polynomial. Then they work through the math to go from an excess Gibbs model, G under bar excess, right? This is the excess Gibbs of the total mixture, is some function, and then you calculate the activity coefficient based on the partial excess, which goes back to the definition of a partial molar property. Right? It's no different than H over bar, even though it's excess or not excess. Okay, yeah, so that covers more or less what I wanted to go over for liquid-liquid equilibrium. We kind of touched on all the greatest hits points on that. Any questions before we move on to some other topics? Okay. So let's do a, let's see. Do you want to start generally? Well, let's just jump into the vapor-liquid equilibrium, which is where we spent a good portion of our class. So, of course, our governing equation is that the partial fugacities of the vapor phase for every species in the system is equal to the partial fugacities of the liquid phase. So if we have a three-component system, we have three fugacity relationships. For the vapor, right, we can write this in a number of different ways. The most common way that we have used is what we call the Lewis-Randall rule. Where we just weight the individual pure species fugacities to get the partial fugacity. Now what we've neglected here is sort of any excess mixing properties. This was derived based on the excess volume, not over bar, just the excess. That if I add 1 liter of gas 1 to 1 liter of gas 2, it stays as 2 liters. But if we have some interaction between those gas molecules, we can't simply use the Lewis-Randall rule. That question?
Correct me if I'm wrong, but the reason we can use this is most gases in a lot of cases are at low pressure, and so the molecules do not frequently actually get close enough to interact like they do with like a liquid, right?
Yes. So in general, if we're going to consider one non-ideality, it's more likely we're going to consider the non-ideality in the liquid phase. But the key thing to keep in mind is that in going all the way down to, let's say, Raoult's law, in Raoult's law, not only are we assuming ideal mixtures of the liquid and ideal mixtures of the vapor, but we're also assuming ideal gas behavior in the vapor phase as well, which is not necessarily always going to be the case. But for most of what we covered, yes, we talked about just breaking it all the way down to the fugacity is equal to the pressure, which means that the fugacity of the liquid is the saturation pressure. But if we were to look a little bit more detailed, we could write that the fugacity of species I in the vapor phase is equal to Y fugacity coefficient times P. Now this term here contains a lot more of the information. Right? This includes the non-ideality of the mixing of gases, right? The fugacity coefficient. So in this case, the partial fugacity coefficient is defined as partial fugacity. Again, it's similar to the activity coefficient approach where you're kind of just cheating a little bit. Because if you were to substitute this back in there, you would just get that the partial fugacity of I is equal to the partial fugacity of I. But this gives us a pathway in to insert a correlation or something of those sorts. But the key thing to remember is that going from this relationship here all the way down to the approximation of Raoult's law, we have to make a number of assumptions, right? Number one, we're going to go from, so if we're going to go to Raoult's law, I think I spelled that wrong, whatever. First assumption, ideal gas behavior, which means that the fugacity of the pure species is just equal to the pressure. Ideal mixing, in which case that the partial fugacity is just going to be equal to a mole fraction averaged fugacity. So if we put these together, then we get that the partial fugacity in the vapor phase is YIP. And that's what we've been using a lot for all the ideal calculations. Now for the liquid phase, we're adding on low pressure, pointing, right, the pointing correction, not 0, is equal to 1, sorry. actually, so if we combine basically all of this, this tells us then that we have and that's how we reestablish Raoult's law. But we could steer this approach off at any step along the way. Right? We have to have, a good 4-ish assumptions before we can even start to get to the Raoult's law behavior. But we can break away with any of those. Right? We could say that we have non-ideal pure phases, but ideal mixing, in which case we would have an activity coefficient, but that the fugacities wouldn't be equal to pressure. Right? They would be equal to the fugacities of the pure species. Right? Or a lot of the work that we've been doing so far is saying we're going to have an ideal gas phase but non-ideal liquid phase. Right? That's going to be more common than, of course, having a ideal liquid and a non-ideal gas, but who knows, maybe it's possible. Less likely, because you would expect that the liquid phase would be the one that has the non-ideal mixing. So the key thing, right, with vapor-liquid equilibrium is that set up your equations, do your degrees of freedom analysis, and it's just a matter of what information do you have, what information do you not have. The standard calculation, like the standard flash calculation, is you're given the temperature and pressure, and you have to solve for the x's and the y's. You take those x's and y's, you put them into a material balance, and you get the total amount of phase 1 and the total amount of phase 2. Right? Phase 1 could be a liquid phase, phase 2 could be a vapor phase. Right? You could do a liquid-liquid flash calculation. That's totally fine as well. Right? These are all valid calculations. We've talked a lot, and you guys generated a ton of TXY and PXY diagrams. So if this is a TXY diagram, I always like to take my time to think about this. So component 1, which I've drawn on the x-axis, is the more volatile of the two species. So should the TXY be kind of generally going down to the right or up to the right? Which is...
More volatile with no down. No, it's going to go
The TXY should go down to the right, because the boiling point for pure component 1 is lower than the boiling point for pure component 2. So in the ideal TXY diagram, it usually looks a bit something like this. I'll draw that. There you go. Now, the bigger the volatility difference is, sort of the bigger this phase, this two-phase region is going to be. If you have two things that are very, very similar, right, you can just get a teeny little sliver potentially, which means it takes a lot of phases, a lot of stages to separate the two of them. Now, this is, of course, for an ideal situation. So at high temperature, what phase are we in? High temperature in which phase? Vapor. And this is the bubble. So this top line here, which is this curve? Dew curve. And this one here is the bubble curve. Oops. Does anyone have any questions on TXY and PXY diagrams? Right?
Because usually it's all in the TXY diagrams that we have to do, even a short one on a test where we calculated points. We probably wouldn't have one of those because they usually to solve for T, then you need to use a solutions method or iterative process to solve them.
So it's much easier for me to ask you to generate a PXY diagram than a TXY. And that is because if we go back to our governing equation, this is, of course, for Raoult's law. The vapor pressure is an exponential function of temperature, which means that no matter what, the TXY diagram is always going to involve some nonlinear solution. In theory, back in the olden days, right, maybe you just had tabulated data of the vapor pressure, in which case generating a TXY was an iterative process. You would guess a temperature, check. Guess a new temperature, check. And if you only have tabulated data, then you're, of course, stuck with a guess and check approach. But this is why a lot of thermodynamic relationships we really, really push to get a continuous function. So that's why a cubic equation of state is so very valuable. There's no magic physics that decide why a cubic equation of state has to look like a cubic equation of state, but it is the simplest equation that we can generate that reproduces the properties of real fluids. And then we've come up with systems to manipulate that equation to tell us how the phase behavior works. That's because if we have an equation, that means we can plug it into a system of equations, we can run it through a nonlinear solver, and we can get numbers out explicitly. So that's why, for the vapor pressure, Antoine's equation is so very useful. Right? It's just a correlation, but it has a semi-empirical basis or a semi-theoretical basis. Right? The exponential functionality is a direct consequence of the Clapeyron equation. But the reason why it's so very convenient to have a continuous function is because then we can solve it. Because if we have to rely on tabulated data, then everything we look up, you look up a number in a table, you do your math. You look up a different number, you do your math. Right? So a lot of these decisions that were made are made out of convenience. The cubic equation of state is a very good example of that. Right? There's no law of thermodynamics that says you have to use a cubic equation of state. Right? It's just the easiest one that shows all the properties that we know how to manipulate. Okay, so we spent a lot of time on TXYs, PXYs, non-ideal, ideal, right? So let's just do a really quick, let's do a non-ideal PXY diagram just to get it out of our system, and we can ask any lingering questions that we might have on it. Okay, so this is a PXY, it's going to be non-ideal. So on the right-hand side at pure species 1, should it be higher or lower? Higher. So PXY is basically exactly the flipped. Right, because pure species 1 has a higher vapor pressure or a lower boiling temperature. Now, if it's non-ideal, we can have lots of different non-idealities. The ideal scenario is where we have a bubble curve that is linear and a dew curve that is nonlinear. Okay, this is ideal. We can have a non-ideal one that might look something like this. Totally fine. The only thing that makes it non-ideal is that it doesn't follow Raoult's law. Does the blue curve have an azeotrope?
This one doesn't have an azeotrope.
This one does not. But so you can be non-ideal and not have an azeotrope. That is totally okay. Now, if I draw one that does have an azeotrope, it should look something like this. Not my best artistic rendering, but we get the point. How can I tell where the azeotrope is?
Where x1 equals y1.
Right, so there's a number of different ways. In theory, this is where the azeotrope is, and this is where I should have drawn the minimum, so where dp dz is equal to 0. That's the formal mathematical approach to determining where the azeotrope is. And so you can also tell that there's an azeotrope when the bubble curve and the dew curve come together and they pinch at what they call a pinch point. So what's this curve here called? What's that one? Which curve is that? That is the bubble, you're right. How can we tell it's a bubble? Because this at high pressure is all liquid. As we lower the pressure, eventually we're going to hit a bubble curve. So regardless of how funky the TXY and PXY diagrams look, if you're a vapor and you transition to a liquid, that's the dew curve. If you're a liquid and you transition to a vapor, that's the bubble curve. Now, if you were to go right across the azeotrope, your multi-component system would be behaving exactly like a pure species, right? Because you would be boiling exactly the same liquid composition to exactly the same vapor composition, and the bubble point and the dew point are exactly the same. And that's exactly what you would observe as a pure species on either of these 2 points, right? So an azeotrope, basically a multi-component system, behaves like a pure component system.
So, it kind of comes back to the governing equations, like where, P bubbles, some xi times P, xat, say, the same goes with the 2.8, they both have to equal the same P plus
So if we
a single component.
yeah, so if we apply, let's say, modified Route's law, xi at the azeotrope, right, these two cancel out. So then this relationship would have to hold true at the azeotrope. But there's a number of different ways you could think about manipulating this. So you could use an azeotrope to tune an activity coefficient model. You could use it to, well, that's the most important one, I guess, is tuning that. But the key thing that we talked about with breaking the azeotrope is that we have control. So we can control the pressure very easily. We can't control the saturation pressure or the activity coefficient, right? That's just dictated based on the mixture properties themselves. So we can change the temperature or we can change the pressure. Now, changing the temperature and pressure might alter how the two materials interact, right? Maybe they behave differently and their activity coefficient model changes when you change the temperature or the pressure. Conversely, we can control how the pure species properties behave by changing the pressure or changing the temperature. And even though they might satisfy this balanced, delicate relationship at one condition of the separation, both of these two curves probably aren't going to have the same heat of vaporization. They're not going to have the same vapor pressures as a function of temperature. And so by playing around with the system conditions, we can shift and move the azeotrope a little bit, sometimes more easily than others. Right? So the strategy that we mostly talked about for breaking an azeotrope was to shift the pressure of the distillation column. But there's other approaches too. Right? In some systems, you can actually add in an azeotrope breaker, which alters the thermodynamics, in which case you're modifying the activity coefficient model. I think you can add in benzene maybe to break a ethanol water azeotrope. I think. You wouldn't want to do it if you're actually trying to consume the ethanol. But I think you can add in third components that alter the thermodynamics as well. Yeah. But basically, so there's lots of different strategies. We talked about the simplest one, which is just shifting the material properties. But with all these multi-component equilibrium problems, they get to be very complex. So designing, let's say, like a liquid-liquid separator, where you're trying to get one solute to partition from one liquid to another, the math for predictive sense gets quite complex, and they have to be kind of designed on a one-on-one individual basis for these processes. Yeah?
When we're doing like flash calculations, we have KI equals with yi over xi,
Mm-hmm.
which in ideal case would be your saturation pressure or system pressure.
Mm-hmm.
When it's in a non-ideal liquid, is it the activity coefficient times the pressure, saturation pressure divided by the total system pressure?
Yeah, so the KI approach, KI is what we call the relative volatility. And so this is going to be your vapor mole fraction divided by your liquid mole fraction. So higher K values in a mixture mean that that's the component that's most likely going to be vaporizing first, or at the highest concentration. And so if we just rearrange modified Route's law, then this would be like this. And it's just a mathematical substitution. It doesn't fundamentally alter your equations or the degrees of freedom or anything like that. It's just a way to help kind of simplify the math if you're doing it out algebraically. And you might find some thermodynamic papers will tabulate relative volatilities as a condensed form to communicate the VLE data. But it doesn't alter the basic premise of what we're working on to use the relative volatility. Because we talked about a specific strategy to solving multi-component flash calculation. When it's two components, it's pretty easy. You can kind of just figure it out and manipulate the equations. When it's three components, it's not quite as clear how to algebraically manipulate them, but using the relative volatility was a nice convenient tool that we employed. So this is just a substitution. And there's a lot of different substitutions, and that's why the equation sheet has a lot of different stuff on there. So we've got a little bit, actually no, we have hardly any time left. But just as a reminder, a flash calculation is we are solving our equilibrium and material balance at the same time. So in a vapor-liquid flash calculation, we're calculating the x's, the y's, and the total amount of liquid and the total amount of vapor. But we could also do a liquid-liquid flash separation, in which case we're calculating the composition of the liquid phase 1, liquid phase 2, and the total amount of phase 1 and phase 2. Whereas when we did the bubble and the dew curves, we only calculated the bubble and dew points. We didn't calculate every single point in between the two of them. So please remember how to do that. Let's see, azeotropes, distillation, we talked about. We didn't do an XY, but hopefully you remember that. Liquid-liquid, we covered that. And then for chemical reaction equilibrium, just to reiterate, be familiar with the approach that we kind of talked about, where you have a table, right? Species A, species B, species C. You could have an inert, right, in a chemical reaction equilibrium. You have an initial number of moles. You have a number of moles that's going to be a function of your extent of reaction. You're going to calculate a mole fraction, in which case here you'll have total Ni. This should sum up to be equal to 1. And we take all these yi's and we plug them into some sort of a model. Right, the reaction equilibrium approach that we take is fairly algorithmic. We didn't talk about really many non-ideal calculations. But in general, right, you were provided a table that has different approximations for the activity. Right, and there's a lot of reasonings behind why we simplify everything down into activity. As bad as we are at predicting all the other material properties, we're even worse at predicting reaction properties. Right? We have no good definitive way to know what is the energy of a CO bond versus a CH bond. Right? Now with quantum mechanics, we can get some sort of an estimate on it. But from a classical perspective, we just have to measure these things. So instead of measuring the reaction at every different possible system condition, we just said, you know what? We're all going to measure the reaction conditions at one temperature and one pressure. 25 degrees C and 1 atmosphere, or rather 1 bar is the more appropriate term. And say, you know what? If you're going to measure reaction conditions, do it at that condition. Then we can tabulate everything and we'll just calculate all reactions going through that point. So the whole premise behind the system for reaction equilibrium is based on the fact that we said, no, just calculate it based on 25 degrees C and 1 bar pressure. With thermo, it's path independent. So we can go down to the pressure, that temperature and pressure, react our system, and go back up to that temperature and pressure. And so the system that we worked out in terms of activities and equilibrium constants, it all supports that system. So if we want to know how the equilibrium constant changes as a function of temperature, we know it's related to the delta H of reaction. But there's a lot of math that goes into it, but just be familiar with the system of setting up a reaction calculation. Right? But so we didn't cover any non-ideality in that, so just focus on ideal reactions for that purpose. All right. Any questions before we call wraps? Yeah.
You get cheat sheet again?
Yes, 1 page front and back cheat sheet. You get the equation sheet. I haven't modified the equation sheet at all. Go back, look through, be familiar with the equations that are there so that you can rely on it and don't have to reproduce it on your cheat sheet. All right, if not, we have office hours at 12 today and 2 tomorrow. So please let me know if you have any questions.